Hello. Now we will calculate the energy stored in the capacitor. Okay. So ultimately, when the energy will be stored, it will be stored against some work done by the external agent. In this case, the external agent is the battery. So obviously some battery will be connected to these two terminals, and that battery will be pushing the charge across this capacitor. And while doing so, that battery will be doing some work done, and that work done will be stored in this capacitor as its potential energy, or you can say electrostatic potential energy. Okay, so we are going for a general point, meaning I am looking at t is equals to t some general time. So at a general point of time, the voltage across the capacitor I am defining as VA minus VB. So at some general point of time, this capacitor is already being charged till charge Q. So the charge across the capacitor is Q, and the capacitance of the capacitor is C. So in that case, the voltage at that instant across the capacitor will be Q by C. Okay. So at this time, now in further dt time, that battery will push some dq charge across the capacitor. Some extra dq charge will be pushed by the battery across the capacitor, and the work done in pushing this charge, dq charge, across the capacitor by the battery will be equals to voltage across the capacitor multiplied with charge which is being pushed by the battery. So that will be the work done by the battery while pushing the charge dq in dt time. Okay. Now this work done will be stored in the capacitor as its electrostatic potential energy. So this is the work done, and I'll be writing it as du. C. C stands for capacitor. So that much work done will be stored in the capacitor as its electrostatic potential energy. So we can see du will be equals to V dq, where V is VA minus VB. This is V. Now let's write the value of V here. It will become Q upon C dq. That will be duc. Now to calculate the total potential energy which is stored in the capacitor, we will have to integrate this. So upon integration, we will be integrating this duc, integration of, and 1 upon c, integration of q dq. So initially the charge, battery is completely discharged. So I'm saying the charge is 0, and potential energy stored is also 0, obviously, since there is no charge. At some general point, or I should say at the equilibrium, the charge across the capacitor becomes Q, and at that time potential energy stored will be UC. So when we'll integrate this DUC, the integration will be, you see, from 0 to maximum, and that will be equals to 1 upon C, integration of Q dq will give you Q square upon 2. Limits from 0 to capital Q. We'll write the values, so it will become UC is equals to half Q square upon C, or this is, half Q square upon C minus 0, or you can say UC will be equals to Q square upon 2 times of C. This is the potential energy stored in the capacitor when the charge across the capacitor is Q. Okay. Now see, we have a relationship between the charge, voltage across the capacitor, and the capacitance. So since we already have a relationship, that is Q is equals to CB, where V is the voltage across the capacitor. So if I replace this value, we'll have one more formula for electrostatic potential energy. So it will be C square B square upon 2 times of C, and that will give us 1 by 2 CB square. Or what we can do, C, and we can take 1 V from here. So CV can be written as Q. So that will become half of Q times of V as well. So now we have 3 formulas for the electrostatic potential energy stored in the capacitor. One formula is in between Q and C, one formula in terms of C and V, and one formula in terms of Q and V. The thing is, when we talk about capacitor, capacitance of the capacitor is a constant. So once you choose the capacitor, C becomes constant. So out of these 3 formulas, these 2 are the formulas which we generally use. Because in this case, this is a formula for potential energy as a function of Q, and this is the formula of potential energy as a function of V. And to be more precise, generally when the capacitors are in series, when the capacitors are in series, in those cases we use this formula for series combination generally. Reason being, when we have capacitors in series, the charge across each and every capacitor is same. So when the charge across each and every capacitor is same, in that case we can compare among the energy stored in each and every capacitor because the charge will be same there. So that energy stored in each and every capacitor in series combination will be inversely proportional to the capacitance. And as you can see here, when we have the parallel combination, so in case of parallel combination, voltage across the capacitor is same. So we use this formula. So this formula is being used for the parallel combination, and this formula is generally used for series combination. So these three formulas are there. One should memorize all three formulas, and this is the derivation, how we calculate the energy stored in capacitor. Okay, I hope you understood this. Thank you.